Hello again. Let's take a look at the concepts of one-to-one and inverse functions. One-to-one and inverse functions. All right. So what do these concepts involve? Well, let's talk about one-to-one functions first. If you recall, a function is a mapping from the domain set to the range set, right? So we have a set of domain values that were, such as, for example, test scores that we're going to map to letter grades, for example, in the range, right? So function maps domain elements to range elements, right? Now, a one-to-one function takes each unique domain into a unique range. Let me say that a one-to-one function maps a unique, keyword is the word unique domain element to a unique range element. Unique range element. Now, earlier in the semester, all right, again, keyword being unique. When we map letter grades, test scores to letter grades, that's not a one-to-one function, right? So, for example, let's say this was letter grades here. I'm sorry, not letter grades. Test scores. Sorry about that. Test scores, right? That was the domain mapped to letter grades. Yeah, this is not one-to-one because, for example, you can have a test score of 75 and a test score of 72, and they're both going to be mapped to what? Letter C grade, assuming a standard 10% scale, in the range. So you have two different domain elements. These are unique, right? These are unique means these are different, but they have the same range, which is not unique in this case. So the key is the range has to be different as well, all right, in order to be a one-to-one function, all right? So then what's a one-to-one function look like then? Well, first of all, the x's have to be different, and the y's, again, range of the y values, right, have to be different. In fact, let's take a look at a more specific function we've seen in the past. Let's look at the absolute value function. Now, we've seen this, right? This is the V-shaped graph we had earlier, right? Now, I'm not going to graph yet. Let's make a table here to help you see that why this is not a one-to-one function. Because if I pick x to be 0, certainly the function value is 0. If I pick x to be 1, function value is going to be 1. So far, so good, right? The domains are different. The ranges, they also map to different ranges, right? So that's fine. But look at -1 now for x. What's the absolute value of -1? That's also positive 1. So we have two unique domains going to what? The same range. So this makes it not a one-to-one function, not a one-to-one function. Because we have 1 going to 1 in the range and -1 in the domain going to also 1 in the range. So again, two different domains going to the same range is not a one-to-one function. In fact, if we were to graph this V-shaped graph again, here's 0, 0, the origin, right? 1, 1, and -1, 1, right? So we have this V-shaped graph we saw earlier, all right? So this is not a one-to-one mapping. Now, in fact, if you look at a test called the horizontal line test, then we can show that this is not a one-to-one function using the horizontal line test. Because if I draw horizontal lines that cut through the graph, remember we have the vertical line test for functions, right? If you cut through the graph more than once, it's not a function on the vertical line test. But if it is a function, so this passes the vertical line test, right? But this does not pass the horizontal line test, because if I draw a horizontal line, I can cut through the graph more than once. So that makes it not a one-to-one function. So the horizontal line test is used to test if a function is one-to-one or not. So let me say use the horizontal line test to see if f of x, if a function is one-to-one. All right, so the horizontal line test. If you cut through the graph more than once, that means it's not one-to-one. Let me give you another graph. Let me cut off the screen. Here's a graph we've seen in the past, right? Let's say this graph looks something like this. All right, this is a parabola, right? Quadratic function, right? So is this one-to-one? Question mark there. Is this one-to-one? Well, again, if you draw a horizontal line there, obviously you cut through the graph more than once. So the answer is no. Not a one-to-one function. So parabolas, quadratic functions are not one-to-one. Can we see that? Let's take a look at this graph here. Here's one we've seen in the past as well. Starts at the origin and goes something like this, right? This is the square root function, if you remember, right? And is this one-to-one? Well, if I draw horizontal lines, I do cut through the graph only once. So yes, this is a one-to-one function. So the square root function, or the square root of x, is a one-to-one function. In fact, if you look at the square root of x in detail, let's let f of x be the square root of x, right? So if we're making our table here of x and function values, right? Again, we can only take square roots of 0 or positive, right? So pick 0 for x. What's the square root of that? 0. Pick 1 for x. What's the square root of 1? 1. All right, no big deal. Pick 4 because that's a perfect square, right? Square root of 4 is what? 2. Pick what? What's the next perfect square? How about 9? What's the square root of 9? 3, right? Square root of 9 is 3. So look, you can see that all the x's are different, all the y's are different. So in other words, if the y coordinates don't repeat, right, then it is a one-to-one function. This is a one-to-one mapping. Right, the key is what? All the y's have to be different. Of course, the x's have to be different to be a function, right? But the y's have to be different as well. It has to be unique, right? In other words, the function values cannot repeat, or the y coordinates cannot repeat. All right. So the square root of x is a one-to-one function. All right. So we can use the horizontal line test again to test whether a function is one-to-one or not. All right. Now, what's important about one-to-one functions is that they have what's called inverse functions. So let me say that only one-to-one functions have inverses. All right. Now, what does that mean? An inverse function. Let's talk about that. Let me go and clear up the screen. Let me give you two particular functions to study here. Let's let actually we don't. That's not really an example, but let's suppose f of x is equal to something like x plus 1 cubed. So cubic function here, right? Let's let g of x be the cube root of x minus 1. And the minus 1 is outside of the cube root. That's a 1 right here. All right, outside of the cube root. So now let's make a table for both of these functions here. I'm not going to graph it. I'm just going to make a table. So let's create tables for these functions. X and f of x. All right, and also x and g of x. All right. Now let's pick x carefully to plug in. All right. So for example, let's pick x to be, say, 0 here. That's a good number to plug in. 0 plus 1 is what? 1. 1 cubed is what? 1, right? If we work it out carefully. What about when x is 1? What's 1 plus 1? 1 plus 1. So focus on the f function for right now. We'll look at the g function, which is a little bit more complicated in a moment. All right. So if x is 1, 1 plus 1 is what? 2. So you get 2 cubed, which is what? 8, right? 2 cubed is 8. What if x is 2? All right. 2 plus 1 is what? 3. What's 3 cubed? So you get 3 cubed. That's 27. It's getting big now. Let me try some negative numbers. Negative 1 for x. Negative 1 plus 1 is 0. So 0 cubed is still 0. Let's try negative 2 for x. Negative 2 plus 1 is what? Negative 1. So what's negative 1 cubed? Well, negative 1 cubed is still negative 1, right? Negative 1 times negative 1 times negative 1 is negative 1, of course. Let's do one more. Let's do negative 3 for x. So what's negative 3 plugged into the f function? Negative 3 plus 1 is what? Negative 2, right? So that's going to be negative 2 cubed. That's going to be what? Negative 8, if we work that out carefully. But as you can see, Of course, my x's have to be different. So since this is a function, but look at my y values. Look at my function values. Are they all different? Well, yeah, yes they are. They're all different. So this function, x plus 1 cubed, is one-to-one function. One-to-one function. This is a one-to-one function based on my table here. All right. Now let's take a look at the g function. Let's create this g table more carefully because I need to pick perfect cubes here because I'm trying to take the cube root of it, right? And then I'll minus 1 from it. All right. So let's do that. Let's pick here. Let me choose the x for you just to make it coherent here. Let me go ahead and pick x to be 1. Let's pick x to be 1 here. Let's plug it in. What is the cube root of 1 minus 1? Let me do the math. Cube root of 1 is what? 1. Cube root of 1 is still 1. Minus 1 is what? 0. Right? Let's pick x to be 8 because that's a perfect cube, right? What's the cube root of 8? All right, minus 1. Cube root of 8 is what? 2 minus 1. That's 1. All right. Let's pick 27 for x. Again, perfect cubes, right? So what's the cube root of 27 minus 1? That's going to be 3 minus 1. Or what? 2. Can we see that? Let's pick 0 for x. Because cube root of 0 is going to be 0, right? Minus 1, you're going to get negative 1, of course, right? That's just 0. Let's pick negative 1 for the x. Because that's a perfect cube as well. Because the cube root of negative 1 minus 1. Cube root of negative 1 is negative 1, right? Minus 1 is going to be what? Negative 2. All right, can we see that? Let's do one last one here, negative 8. Negative 8. Cube root of negative 8, that's a perfect cube again, minus 1. What's the cube root of negative 8? That's negative 2 minus 1, or negative 3. Can we see that? So look at this function, the g function. The cube root of x minus 1. Is this, first of all, it's a function because all the x's are different, right? But look at my y's as well. 0, 1, 2, negative 1, negative 2, negative 3. These are all different also. So this is also a one-to-one function. So both of these guys are one-to-one functions because all the ranges are different as well for the g function. All right, now, but look at the relationship between these two tables, though, most importantly, right? In the f function, my order pair was what? 0, 1. But my g function, what's the order pair? 1, 0. Can we see that? 1 for x, 0 for y. Here it was what? 1, 8. 1, 8 is the next order pair. What's this one? 8, 1. But I think you're starting to see the picture, right? Here it was what? 227. Here was what? 27, comma 2 for the g function. So as you can see, for the relationship between these two tables is that their x and y columns get switched around. In other words, the domain, here's the domain for f of x. So this is the domain of f of x. The domain for the f function is now what? 0, 1, 2, negative 1, negative 2, negative 3, right? Same thing here, right? Is now the range of the g function. And the domain of the g function becomes what? 1, 8, 27, 0, right? 1, 8, 27, 0, right? Becomes the range of the f function. Again, the domain of g becomes the range of f. The domain of f becomes the range of g. In other words, these two tables have range and domain switched around. When that happens, then these are called inverses of each other. So f of x and g of x are inverses of each other. So when two functions have range and domain switched around, then they are inverses of each other. All right. So if I were to ask you to find the inverse, then it's not too bad because all you have to do is what? Switch the range and domain around. Let me give you an example of that. Let me go clear out the screen. Suppose I give you this one-to-one mapping here. Let's say x, f of x. All right. Let's say this was 1, 0, 2, 5, 3, 9. All right, for example, right? This is just some function which we don't know what it is, right, in terms of the formula, right? But I want you to find the inverse of this guy, right? So there's three order pairs here, right? 1, 0, 1, comma 0, 2, comma 5, and 3, comma 9, all right? Let's go and find the inverse. Find the inverse mapping. Find inverse, all right? And here's how we write the inverse here. X and f to the negative 1 of x. Now this negative 1 is not an exponent. Again, this is just function notation for inverse. Right? So in other words, we're saying that f negative 1 of x is the inverse function of f of x. Alright? So again, this is not an exponent, right? So in other words, f negative 1 of x is not equal to 1 over f of x, right? Do not mistake that, alright? So again, this is just a mathematical notation for what? Inverse function, right? Inverse function. Okay? So how do we make this table? Well, again, to find the inverse, since all the ranges are different, this is 1 to 1, so it's going to have an inverse, and to find the inverse, you simply what? Switch x and y. So simply switch x and y. Switch x and y. So you're going to get, instead of 1, 0, it'll be what? 0, 1. Instead of 2, 5, it'll be 5, 2. Instead of 3, 9, it'll be what? 9, 3. Okay? As simple as that. No big deal. You switch the x and y around. Right? Now, what does that imply? What implies that it implies that we can find an inverse function using this strategy of switching x and y around. But before we do a problem like that, let me give you the official definition of an inverse, actually. It's based on the composite functions we talked about earlier. Right? So let me go and clear out the screen and give you the definition. Let me say that definition here. Definition. F of x and g of x are inverses of each other if and only if, in other words, this is a strong condition, right? If and only if what? Their two composite functions are equal to each other. So this is the official definition of two functions that are inverses, right? But practically speaking, we simply switch x and y, right? So f of g of x has to be equal to g of f of x, so the two composite functions have to be equal. If you plug one into the other, and vice versa. In general, they're not equal to, right? But in this case, if they are inverses, they will be equal to each other. And not only that, they could be equal to each other and not be inverses, right? I'll give you an example of that in a moment. But their composites have to be equal to x. This is a key definition right here. Alright, the two composites have to be equal to x. Alright, so to verify if two functions are inverses or not, you simply verify their composites being equal to what? X. So here's what I mean by that. Let me give you these two functions here. Let's suppose f of x is equal to 7x minus 4. Let's say g of x is equal to negative 2x plus 2. Alright, question is, are they inverses of each other? Alright? And again, to answer that, we have to use this definition. We have to verify their composites, and both of them, not only do they have to be equal, they have to be equal to what? Equal to just x itself. Alright? So let's do that. So let's go ahead and look at the first composite then. Let's find f of g of x. Alright? This is, if you recall, defined as f parentheses g of x, right? So you're plugging the g function into the f function. You're plugging negative 2x plus 2 into the 7x minus 4. In other words, this is f parentheses negative 2x plus 2. So this is equal to what? Plug this in for x into the f function. So 7 times negative 2x plus 2 minus 4. That's equal to what? Negative 14x. Plus 14 minus 4, which is going to be what? Negative 14x plus 10. So this is not equal to x, right? And we can stop right here and say, look, this definition is not going to work out for these two functions. So are they inverses? The answer is going to be no. Right? They're not inverses of each other. We can stop right here. Now, let's say we try to find the other composite. No big deal. We can do that pretty quickly, right? This is g parentheses f of x, right? Called definition. This is g of what? What's f of x? 7x minus 4. G of 7x minus 4. Plug that into the g function. So that's going to be negative 2 times 7x minus 4 plus 2. this is equal to what? Negative 14x. All right, plus 8. All right, negative 2 times negative 4 plus 2. This is equal to negative 14x plus 10. Again, in this case, you can see that the two composites are actually equal to each other, right? That they both give you what? Negative 14x plus 10. But again, it's not equal to x. That's the most important part. So therefore, they are not inverses of each other. So not inverses. Not inverses of each other. Okay? So again, verify this definition here. Let's try another one. Let me give you this function. How about these two functions? Let's say h of x equal to 4x plus 2. And let's say g of x equal to 1/4 x minus a half. Right? 1/4 x minus a half. Alright? So are they inverses? Are they inverses of each other? Same question. Inverses of v there, sorry about that, of each other. Alright? Well, again, that's an I right there. Sorry about that. Alright, are they inverses of each other? Okay? So again, let's verify the two composites once again. Let's start by finding h of g of x. Alright, so we'll plug the g into the h now. So this is h parentheses g of x with the composite definition. This is h of what? 1/4 x minus a half. Okay, so you plug in 1/4 x minus a half into x into this 4x plus 2 here. So you're going to get 4 times 1/4 x minus 1/2. Alright, plus 2. What's that equal to? Okay, so 4 times 1/4 x is going to be what? X, because the 4's cancel out, right? What's 4 times a half? Half of 4 is what? 2. So minus 2 plus 2. So 2's cancel out, you get what? X. Ah, that's what we want though. It is equal to x. So far so good. But we're not quite done yet. We still have to verify the other composite. So before we say yes to this answer, let's go ahead and find g of h of x. Find the other composite. This is g parentheses h of x. So you're plugging this h function into this g function here. You're plugging 4x plus 2 into this x right here on g. So this is going to be g parentheses 4x plus 2. Alright, which is equal to what then? 1/4 times x, so 1/4 times the 4x plus 2, that is, right? Alright, so times the 4x plus 2, alright, and then what? Minus 1/2, so minus a half. So what's that going to be? Let's work it out. 1/4 times 4x, 4's cancel out again, you get x. What's 1/4 times 2? 2 into 4 twice, so that's 1/2 plus 1/2. Minus 1/2. So the halves cancel out, and we get x as well. So good, we verified both composites are equal to x, so therefore they are inverses of each other. Okay? So again, if you're asked the question, are they inverses, you need to verify the composites. Alright? Now let's talk about finding the inverse. Let's actually find the inverse though, right? Suppose I give you some function, and I ask you to find the inverse. How do we go about doing that? Right? Let's go and try this one. I'm going to clear out the screen here. Let's say I give you a function like this, f of x equal to, let's say, 4x minus 6, and I want you to find the inverse. Find a formula for the inverse function. All right? So how do we do that? Well, the key concept we talked about was switching x and y, right? Because that's the relationship between the function and its inverse, right? The range and domain gets switched around, right? X and y get switched around. So to find this function, to find the inverse function, here's some guidelines. First, let's go ahead and replace f of x with y. So replace f of x with y. All right? So let's let y equal to what? 4x minus 6, because the function value is basically the y value, right? 4x minus 6, right? Second thing we're going to do is what? We're going to switch x and y, right? So let's switch x and y. In other words, y becomes x becomes y. So we get x equal to 4y minus 6. Does that make sense? We switch, have x and y trade places, basically, right? So x is equal to 4y minus 6, right? Switching x and y. Then the third step we're going to do, so this is going to be switch x and y. All right. Second step. Third step is going to be solving this equation. Solve for y. All right. So x equal to 4y minus 6. Let's go and solve for y. Add 6 to both sides, obviously. No big deal. So we get 4y. Let me put it on the left-hand side equal to x plus 6. All right. Divide both sides by 4. Pretty easy solving problem there. All right. So y is equal to what? 1/4 x, right? X over 4 is 1/4. What's 6 over 4? Reduce that to what? 3 over 2. So plus 3 halves. All right. So we found the inverse to be 1/4 x plus 3 halves, but the final answer should be written using this inverse notation right here. So step 4, you're going to say f inverse of x then will be what? 1/4 x plus 3 over 2. Alright, so this is the inverse function we're looking for. Alright, let's try another one. Let me go and clear out the screen. And then we'll wrap things up here. So let's say g of x is equal to, let's say, cube root of x minus 1. Alright, let's go and find the inverse function. Find g inverse of x. Alright, so again, let's let y be the function. Let y be the cube root of x minus 1. We're going to then switch x and y again. Key step here, switch x and y. So y becomes x, and x becomes y. Cube root of y minus 1. Right? And step 3, let's solve for y. So keep these steps in mind. We're solving for y. So x is equal to cube root of y minus 1. That's how do I solve for y? Add 1 to both sides, because that 1 is not part of the cube root, right? So this is going to be cube root of y equal to x plus 1. And just simply cube both sides to solve for y. And look, we saw this earlier in terms of f of x and g of x when I first start talking about the inverse function concept, right? This is x plus 1 quantity cube. So therefore, my final answer, if you remember earlier, my original function for f of x when I first started talking about the inverse concepts, let f of x be what? X plus 1, oops, not f of x, I should say, so apologize for that. Use the inverse notation here, right? But earlier I had the f of x equal to that, though, right? Equal to this thing, though, right? So g inverse, my sketch pad is acting up a little bit, so bear with me. G inverse of x equal to this expression, x plus 1 quantity cube. Remember earlier that this was f of x when I started talking about inverse functions again, right? Okay, so bottom line is what? What's the theme here? Well, to find the inverse, if I give you some function, you're going to let y be the function. So replace this g of x with y, let y be the function itself, switch x and y, and solve for y algebraically, and we have our answer at the end, using the inverse notation as our final answer. Alright, let me go and clear out the screen, give you some prompts to try and post into Blackboard. I'm going to clear out the screen. Alright, so number 1, let's look at these two functions. Are they inverses of each other? Are f of x equal to negative 6x plus 4 and g of x equal to negative 1/6x plus 3 halves, inverses of each other. So you need the composite concepts here, right? You need to find both composites. Make sure it's equal to what? X in this case, if they are to be inverses. Inverses of each other. Alright, number 1. Number 2, let's say I give you this function here, f of x equal to 1/4 x minus 4. I want you to find the formula for the inverse. Find the inverse function itself. So this involves what we just talked about, switching x and y and so on, right? So do that. And last but not least, how about this one? G of x equal to 3/8x plus 5/4. Okay, 3/8x plus 5/4, and again, find the inverse. Alright, so give that a shot and post the answers into Blackboard. Until next time then.